So another thing that we can use integration for, perhaps unsurprisingly, is to find the volume of an object, right? So we've used them to find areas. Volume is just a natural extension of area just into 3 dimensions. So it's a pretty natural extension of it. So there's a few different ways you typically see integration used to find volumes. One way is in multivariable calculus, when you have a function of multiple variables, you can use what's called double integration to find the volumes. But that's a subject more for Math Tools 3. What we want to just look at now is how can we kind of just use the 2D methods, just working with functions of one variable still, and use that to find a volume. So I want to first kind of look at a picture of this. So this is the site called GeoGebra, geometry and algebra, kind of portmanteau there. So you might have used this site before at some point, but if not, it's a typical site. Like I remember using this in high school. So it's been around a bit. It's typically used for geometry a lot of the time, just kind of like studying objects. It's basically just another graphing calculator. But this one, as opposed to Desmos, lets us look at 3D objects. So let's start by looking at a sphere. So if you don't know, the volume of a sphere with radius r is 4/3 pi r cubed. So we want to look at how we can derive that. Okay. So I'm going to make a sphere here. So I'm just going to make it with the center, and then you can make it as large as you want here. So I just brought it out to, I think, 4, but it doesn't really matter because we're going to just keep the radius of it general anyway. Okay. Now, what we can do using integration is we can look at what we call a cross section or a slice of this sphere. Okay. So imagine we just take a slice of the sphere. Because it's a sphere, it doesn't really matter where we do it. But let's go ahead. I'm going to draw a plane here. Again, the points don't really matter because it's just going to be a flat plane, and we're going to intersect them here. So this blue like dotted line here is showing exactly where they intersect. So that's a slice of this object. Okay. So of course the slice of a sphere is going to be a circle, right? If we look at it from the top, that's another way to kind of see what the slice looks like, right? It's just going to be a circle. And again, I put the radius at 4, but I just want to keep it general. So in general, the equation of a circle would be x squared plus y squared, because we're centered at 0. 0, it would be x squared plus y squared equals r squared, where r squared is the, or r is the radius. Okay. So what we can do is we can take that area of the circle, and then we can use integration to then kind of find the area of all of this going up and going down. Okay. So we're going to kind of take that area of the circle and integrate it from the bottom to the top. And that's going to, basically it's going to find the area of this slice, find the area of the next slice, infinitely many slices all the way top to bottom, right? Just like when you're doing it 2-dimensionally, you're finding the like infinite number of rectangles, right? So here we're just using that slice, and then we're finding the area of an infinite number of slices here, and then we're going to add them all up, and that will give us the volume. Okay. So let's go back to the notes then and look at what this would mean mathematically. Okay. So, like I said, the area of a circle would be x squared plus y squared equals r squared. So if you remember the brief section on trigonometry in Math Tools 1, if you were in that class, then you would, remember the unit circle, right? X squared plus y squared equals 1 squared. So it's a circle with radius 1. Here we're just going to keep it general though. So we can do this with respect to either variable. We typically do it with respect to y, of course. So let's solve this for y. So this is going to be y is equal to the square root of r squared minus x squared. And technically it's plus or minus the square root, but it doesn't really matter. We can go ahead and do it that way, but we're going to end up squaring it anyway. So it doesn't really matter. Okay. So this gives us the radius of or specifically if we just look at half of this, then this gives us a formula for the radius of the cross section, the slice, in terms of y. So if we go back to the picture here, because I know it's a little bit weird since we have a radius in there, but what I mean is if we just look at that circle, the blue intersection part here, then the y value gives us the radius as well, right? So like if your y value is like if you're at the point like 0, let me rotate it because I'm on the negative side. If we're looking at the point like 0.4 on this one, for example, right, that is a radius of that circle, right? So we can, so essentially you could do the same thing with the x side. It doesn't really matter. And then, yeah, so anyway, so we want to take that and we want to integrate it from the bottom of the sphere to the top of the sphere, which is going to be negative r to r, because that's what the radius of this sphere would be, right? The radius of the sphere would be the same as the radius of the cross section of the circle. So the formula for the area of a circle, of course, is pi r squared. We're formulating our radius in terms of just the y coordinate here. And again, like I said, there's different ways you can do it. But the idea is that as you go up on the cross sections, like the radius is going to change. So that's why we're not looking at it with just r. Okay, so like for example, if we were to look at a, trying to think of how to move this. Okay, so I just deleted that plane and I made a new cross section here. I don't think I got it perfectly straight, but it's the idea that's important, right? The radius of this cross section is different than the radius of the bottom cross section, the centered cross section we were looking at. So there, r would be the radius, but this is why we want to put it in terms of a formula of either y or x, because as you move up, the radius of the cross section is different, right? It's largest right in the middle, but it's getting smaller as you go up or as you go down, right? But the radius of the sphere itself is staying constant. So we're kind of using two different radii here, right? The radius of the cross section versus the radius of the sphere. So when we go to integrate this, our bounds are going to be the radius of the sphere, which we're calling r, and then this is pi times the radius of the cross section, which is the square root of r squared minus x squared squared. Okay, and again, you could do this like r squared minus y squared if you wanted to integrate the other way. That would be fine too. And we're integrating with respect to x. So x is the radius of the cross section. Okay, so this is the radius of the cross section, or the slice, as we like to call it. And then this is the radius of the sphere. Okay. And at the middle point, like if you look at the cross section right through the center, this is going to be the same, right? But in general, it's not. So we want to then go ahead and integrate this. Okay. So this is going to be equal to, so luckily with the squared and the square root, these will cancel. We could take the pi out of here. Okay. I'll move down here. So we have pi. It's going to be r squared x. Remember, we're integrating with respect to x. So r squared is just a constant. R cubed over 3. From negative r to r. Some people like to just do half of it and then multiply by 2 because it is symmetric. That's fine too. So we're just kind of doing it the long way here. Okay, so we get pi times, what's that going to be? R cubed, because we'll have r squared times r, minus r cubed over 3, minus a negative r cubed, plus a negative r cubed over 3. Okay, I got to be really careful with the signs here. So we'll get pi times, that's going to be 2r cubed minus 2/3 r cubed. Okay, and then 2 minus 2/3 is indeed 4/3. So this is going to be 4/3 pi r cubed. Okay. So we end up with the formula for the volume of the sphere. And you can do this with any object. So it's good to try this on like the common geometric objects where you know or can look up the formula for the volume, just to kind of get a feel for this. But then we can do this with weirder surfaces as well, which we'll see in the next video.